So let's talk about homework 3. So the first problem was about computing the probability that mu minus 2 sigma less than x less than mu plus 2 sigma in two problems. One problem is a continuous random variable and the other one is a discrete random variable. So here you start by finding the expectation, which is simple integral of x times f of x dx. That gives you 1/2. Expected value of x squared is 3/10. So we find sigma squared as the expected value of x squared minus the square of the mean. In this case, you get 1/20. Now you compute mu minus 2 sigma and mu plus 2 sigma. And you need to make sure that you are still within the range of the random variable. Luckily for us, this is larger than 0, which is fine, and this other one is less than 1. So the two numbers are within the range of our random variable. Therefore, the probability that we need is going to be the integral from the smallest of the two numbers to the largest. And that's our density. And that integral gives you this. And then you plug in the two numbers, do some algebra. I refuse to use the calculator because we say we don't use that. And then I get 11 over 5 square root of 5. So for the second distribution, we have.
You say in our place we can use calculator.
You will not use the calculator in the test. I think that's written on the syllabus, right? The reason is simple, because some students are very smart. They know how to program everything on the calculator. Yeah. Problem B, distribution is P of x is 1/2 to the power x. I got someone in the waiting room here. And so in this problem, it's a discrete problem. You need to compute the expected value and compute the square of the expected value. Of course, you need to learn how to do that, because if it's the setup of a test I asked you to find that, I actually need to see how you compute it, not just copy the answer from somewhere. You need to know how to find that expected value. The expected value of x in this case, by definition, is sum over all integers from 1 to infinity, because it starts 1, 2, 3, all the way up to infinity and 0 elsewhere, of k times 1/2 to the power k, because the probability is 1/2 to the power k. And now you need to figure out a way to add this thing. So from Calc 3, we have that the derivative of this power series is the sum k from 1 to infinity. You drop the k, you get k, x to the k minus 1. And you can remove that minus 1 and get outside 1 over s sum. And what is inside here is exactly what you need to add when x is equal to 1/2. So you can solve here and find out that this thing is the derivative of that times x. Therefore, but the derivative of this sum itself is 1 over 1 minus x. And its derivative is 1 over 1 minus x squared. Therefore, you have that this sum is equal to x over 1 minus x squared. And in your case, x is 1/2, so you plug it in here and you get the answer too. Then you compute the expected value of x squared. It's going to be the same game. That's going to be sum k from 1 to infinity, k squared, 1/2 to the k. And then you see you have a k squared here. So that has to do with taking derivative 2 times. So we start here. X over 1 minus x squared. That's what we just found here. It's sum of k times x to the power k, and I need k squared. So I know if I take the derivative of that thing, I'm going to get k squared. So that's what I do. I take the derivative of that. It's sum k from 1 to infinity, k squared, x to the power k minus 1. And I need x to the power k, so I get that power out again, that minus 1 out again. So that's 1 over x, sum of k squared, x to the k. And this is what I need when x is 1/2. So I solve for that as well. It's equal to x times the derivative of x over 1 minus x squared. And I compute this derivative. That's what I get. And I multiply by x. Plug in 1/2. That's the formula. From this formula, I plug in 1/2 for x and find that the expected value of x squared is 6. Then we come down that sigma squared is expected value of x squared minus mu squared, which is therefore 6 minus 2 squared, you get 2. So sigma is square root of 2. Now, in this problem, you got to be careful because you have a discrete problem. So you need to figure what discrete numbers are within mu minus sigma and mu plus sigma. Mu minus sigma, this is 2 minus 2 square root of 2. This is a negative number, right? So the numbers that we are interested in will be starting 0 and up. And the probability even for 0 is 0. So the numbers of interest are 1 all the way up to the last integer below this. This is 2 plus 2 square root of 2. How to do this if you don't use a calculator? How to know when you stop? You take that 2 square root of 2 squared. That's 8. 8 plus 2. No, 8, sorry. 8, it's just before 9, right? And the square root of 9 is 3. So you need to stop before you add 3. So that will be 2 plus 2, 4. So you'll be adding 1, 2, 3, 4. And now you need to use the calculator. That's how you can approximate the integers here to get the number. So 2 square root of 2 squared, that's 8. It's less than 9. Square root of 9 is 3. So we need to stop before 3. So that's 2 plus 1, 2 plus 2, 2 plus 3. And when you get 2 plus 3, you're out of that interval, so you stop. And then you add the 3, you have the probability that you need. At this point, I don't need you to be adding these numbers to give me a final number. Because if you're sitting in here, you're doing a test, you will not be having time to add numbers. Any questions on this page? Is everybody okay with this?
Some test you want us to leave it off that.
Like this, it's
don't
fine.
put together.
It's not worth the time. No questions? All right. Go to the next page. The next problem here was this is the easy part. Show that this expected value is 0 and that expected value is 1. Just use the fact that the expected value is linear. So it's expected value of x minus mu over sigma. and the expected value of x is mu, so mu minus mu is 0, so we're fine. For this one, you get out the x sigma squared, because when you square sigma squared, it's a number. It can come out of the expected value, because you have expected value of x minus mu squared over sigma squared, and that by definition is sigma squared. So you get 1. Now here, when we want to show that this thing is equal to e to the negative t mu over sigma times the moment generating function evaluated at t over sigma, you need to remember one thing. There is a range that is given to you here in that problem that needs to be used. If you are not using it in your answer, you know there is something that is wrong with what you're doing. So if you start the problem, you want to find the expected value of e to the t times x minus mu over sigma. That's what the moment generating function is for x minus mu over sigma. Because t times mu over sigma is a constant, we can take that out of the expected value. The expected value of a constant times a random variable is that constant times the expected value of the random variable. And now I can take together t and sigma as t over sigma. That's a new time. And technically, this is expected value of e to the, and this is the value of the variable times x, which is exactly the moment generating function of x evaluated at the point t over sigma under the condition that t over sigma is between negative h and h, because that's where you started for t. The values of t that we plug into the moment generating function need to be between negative h and h. So if I'm replacing t by t over sigma, it better be between negative and h, and that's why you end up with negative h sigma less than t less than h sigma. So many were forgetting about that. And what we do here is caring about the details, because statistics are about details. Now, the next problem here, I haven't started creating most of you, so I don't know how you guys did on it. No comments. So let me just talk about what I did. So the claim in the problem is that M is a unique median and B is a real number. And we need to show that the expected value of absolute value of x minus b is equal to the expected value of absolute value of x minus m plus twice this integral. The only important thing that is given is that m is the median. You don't know if m is larger than b or m is less than b. It doesn't matter in the problem. So if I want to write down what's the expected value of absolute value of x minus b, the only thing that matters is where is x relative to b? Because I want to remove the expected value, the absolute values. So there are two cases. Either x is less than b or x is larger than b. That's why I gotta split this. When x is less than b, the absolute value is b minus x. When x is larger than b, the absolute value is x minus b. That's the difference between the two integrals. Then you bring in now m, because you need to have integral from m to b. Bring it in. So split this first integral, put m in there. This integral would be integral from negative infinity to m plus integral from m to b. Bring in here m as well. It will be integral from b to m plus integral from m to infinity. This is correct. Then take the two that have m together to see clearly what is going on, because that's the piece that you think you are interested in. And then these two here, you can see that you have x minus b here and you have b minus x here, but the boundary of integration is flipped. So the two things are equal. Therefore, that is twice integral from m to b. That part is simple. We're done. You know, integral from a to b equals negative integral from b to a. That's what we use here to get double. Now we are left with this portion. What's disturbing us about this portion? We need to have the expected value of absolute value of x minus m, right? And just as we did for the case of x minus b, we create that here. What I'm missing here is m. So I'm going to plug in m plus minus m here. One of the m's that is minus goes with the first piece, which is b, and the other one stays with b. So I'm going to have m minus b times f of x, and then where we can get me lost. So I'm going to have b minus m here when I plug in m. So minus m plus m, okay? I'm going to have b minus m. That's this piece. In here, I'm going to do plus m minus m. And so you will stay with m minus b, and then x minus m. The two x minus m, one from here and the other one from here, go into this. And the remainder is this. Are we clear? So, and now the whole issue is about showing that this other piece is actually 0. How do you do that? These are constants. You take them out of the integral. If I take this constant out of the integral, b minus m goes out. I have integral from negative infinity to m. What is m? The median. What's the integral from negative infinity to m? 1/2. That's the definition of the median. So that's b minus m times 1/2. This one is m minus b, and then integral from m to infinity. M is the median. That's also 1/2. Therefore, you get 1/2 b minus m plus 1/2 m minus b, which is 0. Therefore, you got exactly an expected value of absolute value of x minus m plus 2 integral from m to b, x minus b f of x dx. That's for part 1. And the funny part is actually part B. What is the value of d for which we get the minimum? It's easy to guess that d is m, but most of the time people forget how to show that d is actually m for the minimum. How do we show that we achieve the minimum of a function at a point? Because that expected value is a function of d, right? How do we find the point where the minimum is? What's the condition? That's a question for everybody, including those who are online, please. How do we find the minimum of a function that has a derivative, has a second derivative, has anything you need? What's the rule? That was interesting. We love music. So, anyone answering this question, please? You already submitted the homework, so give me what you wrote. How do we find the minimum of a point? How do we find the point where the function has a minimum? Nobody answered this question. Okay. And before that? That's already very far, very far. There are two things. What's the first thing you do when you want to find that? First derivative. How do we call what we do when we find the first derivative here? We find the critical points. Right? You get the critical points, and then you check, you do the second derivative test when the second derivative exists. And this is a problem where obviously the first derivative exists and the second derivative exists. So what you needed to do here was find all the critical points and then do the second derivative test. That's what it's done here. To find the critical points, you needed to take the derivative of that expected value with respect to b. The derivative of the expected value with respect to b, that's the function you're taking the derivative of. This part doesn't have b. The derivative is 0 right here. 2 stays out. This is the integral that has b inside and has b as upper bound. How do you take the derivative? First of all, as if that b wasn't there, you take the derivative of the function of this integral. The derivative with respect to the upper bound is equal to the function that is inside evaluated at that upper bound. So if I take derivative with respect to this b here, I'm going to have b minus b times f of b plus, now I'm going to take the derivative of that thing inside here. Is 1. Derivative with respect to b, it's 1 times f of x, and then integral from m to b f of x dx. That's how you get that derivative. Now this is 0, and you get that the derivative is 2 integral from m to b of f of x dx. And when you want to find the critical points, you set this equal to 0. Because this is a density is positive. The only way that integral is equal to 0 is if these 2 points are equal. That's why b is equal to m. And then you take the second derivative, which will be now the derivative of this, because this is the first derivative. And when you take that derivative with respect to the upper bound, it's just 2f of b. But you know that b is equal to m at that critical point. So when b is equal to m, you plug it in here. 2 f of b. What is f of b equal to? Technically, I think something stupid here. It's not supposed to be that. It's not 1. It's 2f of b, and it is strictly larger than 0 because m being the median, it's surely not at the beginning of the interval where the density is equal to 0. So you can conclude that at b, you have the unique point where you have the minimum of that function. Now, the other way to look at this could be To write f of b, if it's confusing what I did there, you could write f of b equals expected value of x, absolute value of x minus m plus 2 integral from m to b minus x dx minus 2b. Missing something here, right? F of x dx. So I take out the b and integrate from m to b f of x dx, right? Minus 2 integral from m to b x f of x dx. In this case, it would be less confusing taking the derivative than the other one. That's why, because this is the product of two functions. You take the derivative using the product rule. This is just one function. You take the derivative with respect to the upper bound. So f prime of b is equal to 2 and then b times integral from m to b f of x dx. Take the derivative minus twice integral from m to b x f of x dx. Take the derivative. In this case, you will use product rule as I was showing you. So derivative of b with respect to b is 1. So that's going to be integral from m to b f of x dx plus b times the derivative of this integral. And you know that the derivative with respect to the upper bound is the function that is inside evaluated at that upper bound. Does everybody agree with this? So that's going to be f of b minus same thing here. That will be 2b f of b. And now you can see they cancel and you get the same answer that I got here, 2 integral from m to b f of x dx. The property I'm using there is this derivative with respect to x of integral from a to x f of t dt equals f of x. Is there any question? All right, if there is no question, then we move on. Then 1.10, for the couple of problems that I checked, I think people had issues here forgetting again about checking the assumptions. When you say you're using Markov's inequality, you need to check the assumptions of the Markov inequality. If you're using Jensen's inequality, check the assumptions of the Jensen inequality. You don't just claim you're doing it and then you just apply the final formula. So what does the Markov inequality apply to? It applies to a positive function of x, isn't it? So you got to define that function of x and see that it is a positive function of x before applying. Now, so in this problem, we wanted to show that the probability is less than the expected value divided by d to the power 2k. So, and I start by saying, okay, so the probability, because if I put the absolute value here larger than d, this probability is going to be same as the probability of x minus mu without putting absolute value to the power 2k larger than d to the power 2k. Why is that? Because 2k is given. Because if that was an odd number, then this thing wouldn't be correct. And then I define the function u of x, and I want to apply the root. That u of x is x minus mu to the power 2k. It is a positive function. And the problem says that that expected value is finite. Those are the two conditions of Markov's inequality. Positive function of x with finite expectation. Now that I have them, I can apply Markov's inequality. You don't have this, you give me that, I can't give you full credit. You didn't show me you know what the Markov inequality is. The Markov inequality is not just this. The whole thing starting there, with this being the most important part. Because if that was raised to the power 2k plus 1, you would be wrong applying the Markov inequality. Am I making sense? So that's it for number 1. Now for number 2, I think you had issues figuring out how to use the condition that was given, that the probability that x is less than or equal to 0 is 0. Now we needed to show that the probability that x is larger than or equal to 2 mu is less than 1/2. Two things are important here. You need to first assert that mu is not 0. Otherwise, there's no way you are using the Markov inequality with mu. And second, you need to make sure you know that there is no value of the random variable below 0 with the probability, because the probability that anything is below 0 is equal to 0. So if the probability, because the probability that x less than 0 is 0, the probability that x is larger than 0 is 1. And if that's the case, then the expected value is positive, because in this range, x strictly larger than 0, there is no 0. So you can't have a probability, add positive probabilities times a positive number and have 0. That's why that condition is important here. Using here, you end on mu strictly positive. Mu cannot be 0 with this condition. That's why it's there. Otherwise, there are cases where this will be wrong. That inequality that you're writing there will be wrong. Then, because we know this already, we can try to apply the Markov's inequality. And what do I apply it to? I start by absolute value, because I don't want to say anything that I don't know. Nobody really said that there's no value of x that is below 0, right? If they are there with probability 0. So I start probability that absolute value of x is larger than 2 mu using Markov's inequality. The function u of x equal absolute value of x is positive. It has an expected value which is equal to the expected value of x, because the probability that x is less than or equal to 0 is 0. So this thing is positive, and the expected value is finite. Therefore, the Markov inequality applies. And most of all, because this mu is not zero. Therefore, this probability is less than expected value of absolute value of x by Markov inequality over 2 mu, which was there. But I just showed that the expected value of absolute value of x is equal to the expected value of x. Therefore, it's mu over 2 mu, which is 1/2. But I was dealing here with absolute value, but what I need is just x larger than 2 mu, right? So I need to take care of that now here. The probability that absolute value of x is larger than 2 mu is the probability that x is larger than 2 mu plus probability that x is less than -2 mu, right? That's how you handle absolute value larger than a number. Either it's the upper tail or the lower tail, which is at negative, the value that you're checking with. But because probability that x is less than 0 is 0, this probability is 0 as well, because it's a subset of x less than 0. Am I making sense? Therefore, this being 0, the probability here is equal to that, and I show that the first one was less than 1/2, but therefore this is less than 1/2. All right, so any questions on this one before we get to the next problem? All right, 1.104 had to do with moment generating functions. We have a moment generating function that is defined between -h and h. And we wanted to show that the probability that x is larger than a is less than or equal to this quantity. So probability that x is larger than a is equal when t is positive. I say it's e to the tx larger than e to the ta. Why is that? Because e to the tx is an increasing function when t is positive. So the two probabilities here are equal. And now this is my u of x. U of x is e to the tx. It's a positive function with finite expected value. Therefore, by Markov inequality, this is less than expected value of e to the tx over e to ta. But this is the moment generating function. And so we get what we needed under the condition that t is between 0 and h, because here we were dealing with positive t, and from the definition of m, t must be less than h. That's why this condition is there. For the next one, you got probability that x is less than or equal to 0. When t is less than 0, exponential tx is decreasing. Therefore, the order of the inequality changes when you take exponents on both sides. It becomes e to the tx larger than or equal to e to the ax. For the same reason, this is the same function. That's the same function that is defined here. Even for a negative t, it is still a positive function of x, because its exponential is always positive. Therefore, I can again apply Markov inequality. That will be expected value of e to the tx over e to the at, and again, we got this. But we had the condition that t is less than 0, and from the beginning, t must be larger than -h, and that's why this condition applies. Questions? Are we together, Taylor? Okay. All right, now the last one was the easiest of all. So you got phi of x equals log of 1 over x is a convex function. Why is that? Derivative is negative 1 over x. The second derivative is 1 over x squared, which is positive. So we're fine. And therefore, by Jensen's inequality, the expected value of the log of 1 over x is larger than or equal to log of 1 over expected value of x. Okay. And so have we finished with the homework. Any question? I love getting questions, you know. So let's continue working on some conditional distributions as we started last time. 3 more examples. We computed the conditional distribution of x1 and x2 in one example and found the expected values. And we can do more today with other examples. The test is next week, right? Hopefully say so. All right, let's just pick a random problem like this from, yes, finally. Is that? Again, my answer was usually when I present this in class, I don't intend to post them on Blackboard because is it not on the video? All right, anyways, I'm going to post that. Congratulations. So say thank you to her. Yeah, I'm gonna make sure I post that. Okay. So now we good? Is everybody happy now? Because maybe that's the reason why people were so calm. Please, sometimes say something. You got mask. I don't see how what's the expression of your face, and then you don't say anything in class. Oh, like okay. Any questions? Yeah.
Zoom thanks whoever asked that. So
Zoom does what?
Zoom thanks whoever asked about the homeworks to Blackboard.
Oh yeah. They are saying thank you to you because everybody, there are like 7 people there saying thank you to you. So so that's us. We rule, right? So now the problem we're going to solve now is 2.3.2 in case mistakenly you have the book. So let's open the book and we think about this problem all together. So please don't email me this night because maybe I don't have time to do it before I go home, but I will do it before tomorrow, say afternoon. Okay. All right. So problem 2.32. And this is the time where we are allowed to make mistakes, okay? Don't be too harsh. You have the right to have mistakes. Let f 1 given 2 of x1 given x2 be equal to c x1 over x2 squared under the condition 0 is less than x1. I never seen this problem. Why am I picking it? And 0 less than x2 less than 1. And 0 elsewhere. So this is the conditional distribution of x1 given x2. And then f2 of x2 equals, that was c1 here, and then there's another c here, c2. Wow, that's crazy. x2 to the power 4 when 0 is less than x2 less than 1 and 0 elsewhere. So we have these two things. Questions. A, find C1 and C2. I love this kind of problem. So what we do here to find C1 and C2? Hello, we are thinking together here. What's the idea to find C1 and C2? What do you think we should do? The problem says this is the distribution of x1 given x2, and that's the distribution of x2. So what's the property that needs to be used to find C1 and C2? Yes. Huh? Integration of each of them should be 1. Because they are distribution functions, the integral of each of them should be equal to 1. And that's what needs to be used to find C1 and C2. So integral of f1 given 2 of x1 given x2, the x, what x do we need to integrate with respect to? Is it x1 or x2? x1, because x2 is given. That's what is under the bar. x2 is given, so it's dx1. And we are integrating this from negative infinity to infinity. And as we did last time, we're going to go through that integral and make sure that we start when the range starts. The range of x1, that's x1, starts at 0, and it goes all the way up to x2 when x2 is fixed. So it stops at x2. After x2, the value of the density is 0. So the integral goes from 0 to x2 of c1 x1 over x2 squared dx1. And that is equal to c1 over x2 squared, because this is a constant, and we integrate that constant goes out, and we integrate only the thing that depends on x1. And this integral is x1 squared over 2, plug in the values. So that is c1 over 2, because when you plug in x2, you get x2 squared. That cancels with the bottom, x2 squared. And this integral must be equal to 1. You see that the integral does not depend on x2, right? Though x2 was fixed, for every fixed x2, this integral must be 1. And Obviously, we got an answer that doesn't depend on x2. So if you're answering this question for a different distribution and you find out that your C depends on x2, you need to make sure you check the interval that you integrated over. So you did something wrong because the answer must not depend on x2. And that leads to C1 equals 2. So you know C1. And same thing now for F2, integral from negative infinity to infinity of F2 of x2, ex2 this time equals 1 as well, because it is a distribution of x2. This is equal to 1 because it's the distribution of x1 given x2. And so now we want to integrate. What should be the range of integration of this? 0 to 1. You can't say it is x1 to 1 because x2 got to be larger than x1. No, there's no x1 in this thing. And the range is right there for f2, 0 to 1. So it's the marginal distribution of x2, has nothing to do with x1, right? So 0 to 1, c2, x2 to the fourth, ex2. And that is going to be c2 over 5 equal 1. So you get c2 is 5. Ta-da. So we got the two constants. Yeah. Thank you. Thank you. Part B. B says, find the joint distribution of x1 and x2. F x1, x2 of x1, x2. How do we do this? We have the conditional distribution of x1, x2, given x2, and we have the distribution of x2. How do we find the joint distribution of x1, x2? Hello. I'm here. You can't use probabilities when we're talking about distributions. So maybe I'm thinking you are having the correct idea, but saying it the wrong way. What's the definition of the conditional distribution of x1 given x2? Anyone with a proposition? I don't want to be calling names because in this country we have democracy, so the doctor is not supposed to call the student to answer a question if he doesn't volunteer. Huh? It's a definition that I want. It's written in a previous lecture. equal to by definition.
Joint probability of
Not probability, not probability.
Double integral.
Joint distribution divided by the margin. That's the definition of the conditional distribution. From that definition, that's what you get from that definition. The joint distribution is just the product of that conditional distribution and the marginal distribution of x2. That's equal, this is given right there. And C1 is 5, C1 is 2. So that's 2x1 over x2 squared times, and this distribution is C2, which is 5, times x2 to the power 4. So this thing is 10 x1 x2 squared when 0 less than x1 less than x2 and 0 less than x2 less than 1 and then 0 as 1. Yes, I will. So that's what the joint distribution is, and this is what usually we call the support of the vector x1, x2, because out of that range, that vector has probability 0, the density is 0, no value there has a probability. So this would be the joint distribution of x1, x2. Now, the question is, switch the questions, find probability that 1/4 is less than x1 less than 1/2. Now, provided what we know in this question, how would you answer this question? Mind you, the distribution of x1 is not given. And we didn't find it. So how do we find this probability? Use the joint distribution. How do we use it?
It's 1 by 2. X2 bounded. So maximum vector. 1. X2 from 0.
At what point there did you use 1/4 and 1/2? The idea is correct, but the way you're going about it is
Instead of moving to 0, it's like 1.
and now when you want to start at x2, do you know if x2 is less than 1/2 or not? No, we don't.
We're going to use given condition. Given x2 is better.
You're changing now what I already told you was the right thing to do. And if you're changing, then you're going to something that is wrong. We need to use the joint distribution. How? This is the time we're working together. Please, everybody, including the people that are online. How do we find this probability, knowing what we know in the problem? The good idea that was given is that we need to use the joint distribution. I 100%, even 200%, I agree with that. Nothing else. But how do we use it?
Make parts from we check x2 from x1 to respect x1.
You remember what I told you last time? What do we always need to do when we are using the joint distribution and we want to compute some integrals? What do we need to do? What's the first thing we do? It has nothing to do with computing. You do that before you even start thinking of how to compute. Sketch the region. How are you going to compute an integral if you don't even know where the numbers are? You need to sketch the region. If you want to figure out where these numbers stand, if you don't want to find the distribution of x1, then sketch the region. Put this in that region because this is actually same as probability that x1 belongs to 1/4, 1/2, and x2 belongs to 0, 1. That's what it is. Because when you're interested only in x, it means that x2 varies throughout the entire region of x2, which is from 0 to 1, and therefore this probability will be exactly equal to that. And so you need to sketch a graph and see this region in the support. See this region in the support of the distribution that you're using. And see what to integrate. Otherwise, you'll have to find the marginal distribution of x1 before you do anything. Right? So, if we agree with each other, then let me sketch that graph now. We see. Am I late already? Because I see some people checking their watches. Do I still have time? Thank God. So I still have time, right? Thanks. So, how do we do this then? Sketch the graph. Put those numbers on the graph and see what is going on. And what are we sketching? This region. That's the region where x1 and x2 live. x2 is from 0 to 1. So I put that right there. And then this as well tells me that x1 is always less than x2. So definitely x1 cannot be larger than 1 as well. So I'm good to put those two boundaries there. I know that everything has to be living here. And most importantly, here, 0 less than x1 less than x2. So I need this boundary here, x1 less than x2, I need to draw it. And that comes from x1 equal x2, and x1 equal x2 is that line. So now my region is either this or that. What did we do last time to choose? How do we choose the region of interest? Pick a point either here or there and check the inequality. If I pick a point here, that'll be like, say, 1/2 and 1/6. Will 1/2 and 1/6 be here? Where? 1/2 and 1/6 up here? Is it possible? No. I'm just kidding, to be honest. So 1/2, if I'm standing here, definitely it's possible to have 1/2 here for y, but not for x, right? So here, this is x1, and that's x2. So I can have 1/2 here, right here where I'm standing for x1. So it's definitely the x1 will be going to be 1/6. If I'm here, the x1 is definitely 1/6 and the x2 is 1/2. So in that case, when you're there, your x1 is less than x2. Is that correct? So this is the space of interest. Everybody agrees with that? And this is the support. So we call this the support of the random vector x1, x2, which is the region where the density of that vector is not equal to 0. Everywhere else, it's equal to 0. And the other way to check that I got it correct is, say, for this conditional distribution that is given here, it says that when I fix x2, x1 goes from 0 to x2, right? Let me check that here to make sure I got it right. So I fix any x2 here. If I fix x2 here, and I draw a line, as I told you last time, I draw a line through this, what will be the range of x1? 0 to the number that is here, which reflects as x2. So yes, we got the correct region. And now we got the correct region, and we want the probability that x1 is from 1/4 to 1/2. Roll that to get into the region of interest. So that's starting from here all the way up, then starting from here all the way up. So this is the region where you want to integrate. You want to integrate over this region. And if you don't draw, you can't see it. So that probability that 1/4 less than x1 less than 1/2 is nothing but I'm going to integrate from 1/4 to 1/2 because this region is so nice to me. Whenever x1 is fixed, when x1 is fixed, x2 goes from this, right? When I fix x1, x2 goes from this value, which is x1, to that value, which is 1. And then the density is that guy 10 x1 x2 squared x2 and then x1. Okay. Notice that for a different region, you could fall onto a completely different set of numbers here, right? To put it. So now we can integrate this thing. So it's going to be integral from 1/4 to 1/2 of, and this integral is 10/3 x1 x2 cubed x1 to 1 dx1. Okay, coming. So it's integral 1/4 to 1/2. We can put the 10/3 out. And x1 times w1 cube is 1 minus x1 cube x1, which you can integrate as 10/4. Integral of x, that's going to be x1 squared over 2 minus integral of x to the 4th, that's going to be x1 to the 5th over 5. And plug in 1/4, 1/2. That's it. That's how you do. Any questions? Yes.
Could we also use the joint?
That's why when we started, I say if you don't want to find the marginal distribution of x first, then you just draw this and then you do your work. Even if you want to find the marginal distribution of x, you still have to figure out what's the range of y that you need to integrate over. So the problem still remains same. Okay. Other questions? Does this make sense? I really want you guys to please learn how to use this when you're talking about your joint distribution and finding probabilities. You always remember that the probability that a vector x belongs to a set A equals to the integral over the set A of f of x, y, dx1, dx2, dx, dy. That's the definition you always think of when you have a set and you have a joint density to avoid having too much work. Now the other question here, probably the last one, was find the probability that 1/4 less than x1 is than 1/2, given that x2 equals 5/8. How would I do this? So what's the formula that I should use here? Use the conditional distribution of x1 given x2, which is where the problem started. Okay. The original problem started by the conditional distribution of x1 given x2. So this is what you want to use with x2 equals 5/8. So we're going to replicate that here. F1 given 2 of x1 given x2 equals 5/8 is C1 we said was 2 x1 over x2, which is 5/8 squared, with the condition that 0 is less than x1 less than x2, which is 5/8. That's how it actually works when you have a concrete number. So 64 times 228. So probability that 1/4 less than x1 less than 1/2 given x2 equal 5/8 equals integral 1/4 is larger than 0, so we are good. So 1/4 and 1/2 is less than the upper bound of the region of interest, so it's okay. Because in some cases, you have to change. If the number is larger than this, then you have to stop here. If that was 1/4 less than x1 less than, let's say, 7/8, for example, less than 7/8, it's still less than 1, but it's larger than this number. So my integral will have to stop at 5/8 if the number, the upper bound is larger than 5/8. So let's, here we stop at 1/4, 1/2 because it's okay. And then inside we put the distribution that we have, that is 8 squared is 64 times 2 is 128 divided by 25 x1 dx1. So when you integrate that, you get 64/5 x1 squared equal 1/4 equal 1/2. So how much is that? It is something, right? So that is B. But for sure, it's less than 1 because we are talking about a probability, right? So if you find a number that is larger than 1, there is a problem. Find a number that is negative, there is a problem. Any questions, please? Huh? Raise your finger. Okay. All right, so I am under the impression that we have solved enough problems on this topic. I will not be coming back to it anymore. Thank you very much for listening to me today. I see you next time. Monday is the test one, right? Monday is the 20th. Is this the right time to stop or am I early? Is it time?
Dr. Longla, I have a question about the test on Monday.
Yes.
I'm a little nervous. So I know you said that the test questions will resemble the homework problems. Is there any more you can tell us about how the test will work, especially for those of us who are distance?
All right, during the class time, those who are here are sitting here. You guys are sitting there with your cameras on, preferably showing the work you are doing. And when you finish, you take pictures, make a PDF file as for your homeworks and email it to me before you switch off your camera.
Okay.
Is
Will you-
that okay?
Will you be like sending the test to us through like email or like how are we going to get the test?
Yes. As long as we start with, when we sit here and I put everything just as we are sitting now, I will put this on and I will put the test on the screen.
Okay.
Okay, on the screen.
Yeah, we will connect and I will share my screen with the test on it.
Can you tell us about, or if you know how many questions is on the test?
Unfortunately, I haven't seen it yet, so don't worry. It will be just enough for the time. Will be the entire class time.
Okay, because I technically like every day have volleyball practice
Mhm.
during class time. So like right now I'm like at practice, trying to listen in. So I can try and get out of that, but I was just wanting to make sure that I was gonna have enough time to take it.
Now you need to schedule it for the entire class time.
Okay, but you
Class
think
time,
be enough time?
the entire class time.
1 hour 45 minutes.
Okay,
This is gonna chapter 1.
Homework 1, homework 2, homework 3.
Yeah, I think the test for 1 hour 15 minutes.
Yeah.
Is it going to be working or just?
Well, I understand. Sorry, but I didn't even stop this thing from recording. It's still recording.